Hello everyone, this is Devarpan. I will be providing the TA tutorial on the generative adversarial networks or GANs and the diffusion models as part of the course. So I have prepared a notebook which kind of briefly explains the theory that you might have been taught in the course itself already. It covers that briefly so that it becomes a quick recap for you and also helps us to then connect further to the demonstrations and code bases that I have provided with the notebook. So I have tried to follow a basic approach of coding the basic principles of for GANs and diffusion models both, which may not be the state of the art models but gives you a quick start and exact idea about how to implement them. Then further I also talk about the state of the art models that are built upon these basic principles using a lot of large scale data and further engineering tricks and so forth. So let me start now with the generative adversarial networks or GANs. As far as GANs are concerned, let's recap a bit about the theory around it. The goal of the GAN is to learn a generator that can sample a distribution that looks like the real data. So essentially you want to make a data generator, right? It can be a audio generator, it can be an image generator, so which look like the real time data, let's say real time images and real time audios. So you want to make that generator. Let the real data come from an unknown distribution P data X. So X is the real data and P data is the distribution of it. Introduce a latent variable Z which comes from another distribution Pz of Z, usually something like a Gaussian random variable or uniform random variable. Then a generator denoted as G theta Z which has parameters theta, right? This maps the noise Z into a fake sample X tilde which is denoted as G theta Z. So the latent variable you pass through the generator and that returns you the X tilde. Now this defines an implicit model distribution PGX where sampling X from PG is done by drawing first drawing Z from PZ and then computing G theta Z. Now the objective of this generative adversarial network is to train a generated network G theta so that you have PGX that becomes indistinguishable from P data X. Essentially the generator is generating some data X which should be indistinguishable from the real data denoted as P data distribution. Now as we go along, how do you implement it? It should create a discriminator generator game. We introduce a second network discriminator called d phi x which outputs a scalar between 0 to 1 and can be interpreted as the probability that X is real. So essentially you want to make a discriminator that is not able to distinguish a generated data and the real data. So the training becomes a two-player min-max game. Discriminator tries to classify real versus fake and the generator tries to fool the discriminator. The original GAN objective as mentioned in the actual Goodfellow et al 2024 GAN paper. So it's a min-max game and it tries to maximize that the discriminator is not able to classify real versus fake and the generator the generator is generating some image and the discriminator is failing to classify real versus fake. So d phi maximizes this, it becomes a classifier. So d phi should be maximized, at the same time G theta minimizes this, tries to fool the discriminator. So the first term denotes that the discriminator tries to become a better classifier, in the sense it tries to classify real versus fake better. At the same time generator tries to learn in a way that it generates something that the discriminator, no matter how good it is, fails to classify real versus fake. That is the entire idea about this loss function. Coming to the intuition, it is an adversarial game. So two networks are learning together. One is discriminator that learns the features to tell real from fake. On the other hand, there is generator G theta which learns to produce samples that fool the discriminator. Okay. So training alternates are fix first g theta and then update your parameters of the discriminator d phi. The second step, alternating steps are fixed d phi, the discriminator, and then update the generator. So when you reach the equilibrium, then by the construction of it, Pg becomes almost equal to P data. So the real data distribution is achieved closely by the generator's data distribution. And discriminator, if the generator data is very good like real data, then your discriminator fails to classify them as real versus fake. So d phi x almost becomes 0.5 for all samples. It is not able to distinguish. So, but why GANs are hard to train in general? It is a min max optimization. So, it is not a one way optimization. So, it often involves saddle point and leads to mode collapse and training instability and such issues, generator gradient vanishing problems and so on. So, here is a quick and simple schematic of the generative adversarial network. So, you have a corpus of real world images and you sample some images from it, you pass through the discriminator and it should be able to detect it as real. On the other hand, in another branch you have a latent random variable, and that random variable is like z that we mentioned. It goes to the generator and you sample some of it, basically generate some fake samples and then pass through the discriminator and it classifies as fake. Now as the optimization proceeds, the fake images that are generated from the latent variable should not be distinguishable by the discriminator. That is the entire idea, and you employ some loss on it to train these two networks, right. So the coming to the demo of it, we have implemented a MNIST digit generation GAN. We have used simple networks, a feed forward set of layers for generator and discriminator, which will try to generate real looking like MNIST images. MNIST is a data set containing handwritten digits. First we import the necessary libraries, import torch, torch vision libraries and so on. We also load the GPU using torch.device equal to CUDA, and then you also mention the hyperparameters associated with it. Once done, then you also do the necessary transforms that are required, to class, transform the images so that they become normalized and so on, and also processable by the GPU. So you convert them to tensor, also normalization functions. Then you construct your training dataset that can be called from the torch datasets library, datasets.mnist, and also you create a loader function, train loader equal to torch data loader, and then train dataset. You mention the batch size and other hyperparameters that you have defined. Okay. So it gives you, I think, about total number of 60,000 training samples. Now we now recall the principle that we constructed. We have to make two networks, one is generator, another is discriminator, and we will try to learn both of them simultaneously, right. So let us define the generator. It has first a set of linear, it starts with the latent dimension, because it has to remember that if you look at the schematic here, it has to, the generator has to convert that latent random variable to a real data. So for us the images are 28 cross 28, right. So if you flatten it, that becomes that 24 square dimension, that is the image dimension here. Okay. So starting with the latent dimension, you do a set of linear nn.linear layers, and then followed by few activation functions like leaky relu with some hyperparameters associated with it, and then the forward function simply applies self.net, that is this set of layers, and feeds the z, the latent variable, as input and generates the image. Now comes the discriminator. Recall the figure again. What was the discriminator? Discriminator would be taking an image and it would try to classify it as either real or fake, right. So it again involves similar set of linear and followed by activation layers. But what is important here is what is the input and output. So it takes the image dimension as input because it has to take the flattened image as your input, and what is the output dimension? Output is 1 because it will be a simple probability. You remember that discriminator takes an image and calls it real or fake. So it is a single scalar ranging from 0 to 1. 0 means fake, 1 means real. So it again simply then takes x, which is the image, as input and outputs a scalar ranging from 0 to 1. So once you apply the sigmoid layer, that limits any number to 0 to 1. Then you define these networks. Generator is defined using this generator class, discriminator is defined using the discriminator class you have created, and you can print these networks that are constructed now. These are neural networks you have kind of constructed. Okay, they are like this. Then you have to define the loss that you would be using to train it. Remember, here it was. So you would be needing a loss which you will back propagate through the entire thing, and both discriminator and generator will be learned. So the criteria is binary cross entropy loss, because it's essentially a binary classification of real versus fake. The optimizers are defined using Adam optimizers. You mention the learning rate and the decay functions, and then you have to define the noise, that is z, right, the latent variable that you define using a random Gaussian random variable of latent dimension. Finally you create a utility function which essentially just show the generated images. Now comes the training part. So you do multiple epochs, number of epochs you need to iterate the training function, right. So for real images in the train loader, you reshape it so that it's able to fit to the network. You need to create real levels which are 1s, you need to create fake levels which are 0s, and when you feed these real images to the discriminator, that becomes real output. You call it outputs real, and these output reals and real levels you compute the loss on it, which is loss real. Now comes the fake images. You have to generate the fake images, right. So first z is the latent variable you generate from random, which is Gaussian distribution. The fake images will be what? You need to pass them to the generator function. So generator of z becomes fake images. What will be outputs fake? If you pass these fake images to the discriminator, that becomes output fake, and you need to compute loss on them. So you apply that same loss on outputs fake and fake levels. So you get two loss now. One is computed on the real images and another is fake images. So what is the total discriminator loss now? That is sum of the two losses, and you need to do the backward pass so that both networks are learned, and do optimizer dot step. Now you need to this loss d is doing the discriminator update. Now you need to update the generator. So you set the generator to 0 grad, then outputs fake for the generator is, if you feed these fake images to the discriminator that are outputs for the fake images, you can then compute the loss using those output and real levels, and you need to do the backward pass of generator and generator's network. This entire loop, so you can understand that it's doing a sequential optimization, alternate optimization of the discriminator network and the generator network. This loop will continuously iterate, and you should be able to generate real looking images, right. So we have plotted these images, a set of around 16 images. You can see that initially it was, so we are plotting these images that the generator is doing. So generator was initially doing simply images which is like noise, which can be easily detected as fake images. But as the epochs progress, then you can see that these images are slowly converging to the real looking images. Here, so if you go till epoch 5, then you can see that the images look more like real looking, somewhat real looking. You can detect them as somewhat like 8 here, something like 9 here. So this was a basic example of how at least you can see that it's slowly converging towards real looking digits starting from a random noise. And you can use that generator to generate these images, which are more like handwritten generator, not so good, but this is a basic example. With much larger stronger networks, you should be able to get further better images. Then we also do another demo of 2D toy GAN, where we provide two distributions. The actual real-time distribution is a mixture of Gaussian distribution, which is and the mixtures are on the periphery of a circle. So, and we start with a random, completely random data, which is like noise, and then we show that using a GAN, if you train the generator starts to generate data which approximates the mixture of Gaussians very nicely, right? Which will show you that how essentially the underlying distribution mapping is happening. So you can essentially define mixture of Gaussians here. I'll quickly maybe pass through them, and this is the real 2D data, that is the mixture of Gaussians you can have. And then this toy function you need to define the generator and the discriminators in the similar fashion that we already discussed, and similarly the loss function using criteria and then optimizers, and then if you try to train that networks discriminator and the generators, you can see that the fake distribution was starting from here, which was a purely Gaussian noise, and then it slowly starts to converge towards the real data, which is the blue one. And finally you can see that it's nicely converging on the real distribution. So final learned distribution is very close to the blue one. It has clustering on those blue cluster points, mixture points, mixture means, and some around it. So nicely approximates that. So that was about generative adversarial networks training. I hope you got some insight from the theories that you have already learned to actually how to train it. Further, lot of resources you can find online where more sophisticated networks are used essentially to do this approximation better, but I hope this gives you a quick head start and try help you to understand the theory better. That was it about generative adversarial networks. Now we will shift towards another generative model, which is diffusion models. So a quick short theory overview. The diffusion models are generative models again, which will essentially try to learn the real data again in the similar fashion, but in a different process. So it uses a noising process, gradual noising process in learning that. So what happens here? First it involves the forward noising process. So we start from a real data sample x0, that may be an image, and we keep gradually adding Gaussian noise over t steps. Then we define a variance schedule beta 1 till beta t with small beta t. So at each step what happens is that you have steps xt plus 1 like that starting from x0, and it finally should converge to a noise. How it proceeds is that q of xt given xt minus 1. So what will be the next step given the previous step, that is a Gaussian noise, scaled version of the previous step, and Gaussian noise added to it. So it becomes a Gaussian noise with this mean is root over of 1 minus beta t xt minus 1 and the variance is beta t times identity. We can also write xt directly in terms of x0, let alpha t is 1 minus beta t and you define alpha t bar like this, and then you can essentially define what is xt at any step given x0. You can find that expression. So as t increases, xt becomes close to pure Gaussian noise. Okay. You can simply see like as t increases, this root over of 1 minus beta t goes to 0. So this mean becomes 0, it becomes a pure Gaussian. Now that is the forward noising process, but what about the reverse noising process? Then after the forward process is done, the generative process goes backwards. So what we want to do is that given a step xt, we want to predict the previous step xt minus 1. So how the workflow is that in the forward process you start with the real data x and go to a purely Gaussian noise. In the reverse process you start with the noise, come to the real data. Now if you compare with the first principle of the GAN that we discussed about, what was GAN doing? It was starting with a latent variable z, which was essentially a Gaussian noise, and from that it was generating the images, right? So if this reverse process is implemented in diffusion, it will again start with a noise which was the end product of the forward process, and it will do reverse and come to the real data, right? So so in that way both are similar, just that here the process will be step by step iterative denoising, and in that case, GAN's case, it was a min max learning of discriminator and generator. So that generative process, let us see how this reverse process happens now. The generative process goes backwards. We want to start from the noise xt and gradually denoise to get a realistic sample x0. The true reverse conditions are p theta xt minus 1 given xt is normal with pi theta xtt, which is the learned mean from xt and time step t, and sigma theta, which is the learned variance from xt and t. In practice DDBM, we fix the variance and let the network predict the noise epsilon. We parameterize a neural network for this reverse process because it is not a linear anymore. So we define it as epsilon theta. Epsilon is the noise that you want to predict, theta is the parameter of the network that will do that job for you, given the input xt, that is a particular step t image, and the t, that is the time step. So the sampling step is essentially this. So we will keep iterating this from t equal to capital T, which is the last step, down to 1. So we will essentially start from the noise and come to the generated sample x0. How the training objective goes, after we defined xt in terms of x0 using this expression, the training objective is sample x0 from the data distribution, then sample a time step t uniformly from 1 to t, that is all the time steps, then sample epsilon from normal 0 I and compute xt using the formula above, that is the forward process, then minimize the mean square error between the true noise and the predicted noise. So how do we know the true noise? True noise was predicted was obtained during the forward process. You are noising it, right? So during the reverse process you want to estimate that correctly. So you employ a mean square error loss on the true loss versus the predicted loss, a simple regression loss. So this training is very stable. That's the advantage of diffusion model over GANs, that the training is very very stable, minimizing a simple MSE loss, whereas GAN had alternating contrasting losses which made the training very unstable, right. So now relation to the score matching, the network epsilon theta implicitly learns the gradient of the log density of the noisy data distribution, then reversing the diffusion becomes equivalent to following the learned score from noise back to the data. So So this essentially connects the diffusion model to score based generative modeling. Just again, as I told, this is a recap of GAN versus diffusion. GAN was doing a one shot mapping from noise to image as an adversarial game, whereas diffusion is a denoising, step by step reverse denoising to obtain the generated data. So we'll implement a basic version of the diffusion model, but here is a quick schematic, simple schematic of what we discussed. You start with the noise, that is xt. You essentially x0 is the real image. Then in the forward process you keep going towards the xt. So from the original image, that is the right hand side to left hand side, that is the forward process. You keep adding noise so that the image slowly becomes to the Gaussian noise, and in the reverse process you slowly denoise it to get back the S, that is from left to right. Now we will show again one quick and simple demo of diffusion process using DDPM on MNIST dataset, and we will try to see if it is able to generate the images. So we first do the imports of necessary functionalities, define transforms, load in the similar manner the MNIST datasets and data loaders, and then you can define the parameters or hyperparameters associated with the diffusion process, that is like what is the number of steps you want to use, what is the parameter beta want to use, which controls the smoothness of the slow iterative process and all those parameters, and then you define a Q sample, right, which should define the forward function, right. We then simply plot this forward diffusion, forward noising process, forward diffusion. So here are a couple of examples. So every column is an example of the forward noising process. You can see that we start with real looking handwritten digit images which are there in that MNIST dataset, and we start from that and slowly go to the noise. So all of them becomes Gaussian noise. That is the forward process. Now you need to define the reverse process, use this MAC loss and train the network which can estimate the noise from xt and t. So use a we will be using a small CNN that takes xt and t as input and predicts the noise. Similarly, we define all the parameters, data sets. Here are a couple of utility functions to sample the reverse steps, and then we define the simple DDPM using a CNN model. So here are a set of convolution layers, and you define the forward function, which is a set of those CNN layers and ReLU activation functions, and so the job of this DDPM network is to predict the noise given xt and t as input. And you can define finally the loss, which is like MAC loss as we discussed, the noise and predicted noise. Then comes to the training part. You can define the number of epochs you want to train it for, and then the optimizers, and then for couple of epochs you can train that network. So you can define sampling functions and couple of utilities like show samples and reverse process steps, and you can see like the images are generated like this. So of course it's not looking like a very real looking handwritten digits, but this was one quick example on how to code the diffusion model up. So people have tried with a lot of larger networks like UNets to predict this reverse function rather than the simple CNNs, and they have got like good really nice looking images, and it's also easy to train because it does not have unstable training paradigm like the GAN has, right? So one of the cutting edge model using the diffusion paradigm is called stable diffusion, which given a text it can generate the images. So its working looks like this. You have a image X which goes through a image encoder epsilon and gives a variable Z, and then in the diffusion process Z becomes ZT, that is the Gaussian noise, and starting from ZT you have a U-net network which tries to predict the reverse process, and you get the Z back. You can use a decoder which generates the image back again, called X tilde, and further you obviously would not want to generate images just unconditionally. Given some text you want to generate images, like generate images of apples sitting on a table, right? You just don't want to generate random images. So that conditioning is given through this another conditioning network which has the text and semantic maps, or conditioned on images, any kind of conditioning that goes through a encoder and concatenates with this ZT, so that both are passed through this decoding network, and that generates images which is conditioned on this conditioning paradigm. So I will try to show some demos of this stable diffusion model. You can load these, they are available open source using diffusers library in Hugging Face, and you can load them and show some analyze some of the images that are generated given a prompt. So a classroom of student learning about diffusion models, digital art and high quality 4K. So let's see how it generates. So it generates a very nice looking image given that textual prompt. So not only that, you can given lot of prompts like that, and you can see it generally creates very nice looking images. Also you can call a futuristic city built out of data and code cinematic lighting, and there is this concept of guidance scales that is also included in this stable diffusion, where if you can change this guidance scale, and what this guidance scale essentially does, it controls the alignment or conditioning that is happening. So if you increase the guidance, then this conditioning becomes stronger and stronger. The generated image becomes more abiding to the conditioning, right? So here the prompts are essentially conditionings, right? So when you say futuristic city built out of data and code cinematic lighting, and you keep different guidance scales values from 0 to 0, 3, 7.5, 12. So slowly you are increasing the guidance, and what you can see is the first image it generated did not really abide by the prompts specificness. There is no cinematic lighting and all that. So as the scale increases, the conditioning becomes stronger and stronger, and you towards the higher scales you see that really very strong conditioning on the prompt. Similarly, something very interesting is there which is called negative prompts. So you are essentially giving some prompts, but maybe the model might not be exactly abiding by it, or often you want some images that are like negated conditioning. You need a negated conditioning, like you want to generate images of fruits, but you simply don't want images of fruits that contain apples and oranges. So but you are okay with any fruits other than that. So so it's like negative prompt. That provision is also available with stable diffusion. So you can mention the prompts and textual conditionings that you don't want. So you don't want blurriness, you don't want low quality, you don't want distortion, watermark text and all that, ugly, deformed and all that. And what is the positive prompt? That's a close-up portrait of a person, ultra detailed cinematic lighting. So you can see that when there was no negative prompt, it was generating an image, but which might be of not that great quality and aesthetics, but when you use the negative prompts to make it not, when you specifically say that it should not be blurry, it should not be of low quality and all that, you can see that it's getting very high quality images as the negative prompts are more comprehensive and stronger. So yeah, that was about it majorly. So but only thing is that we saw a lot of positives, right? It's getting to a very nice looking images, lot of real looking data and so forth, but the problem we didn't look at. So are they all perfect? Are they generating images which is like perfectly looking and everywhere and all that? No. So when comes to lot of specifics, they miss out a lot. So this is among one of the major drawbacks of these models yet. So for example, if you try to tell it to generate a photo of human hand palm facing the camera, right, it generates a lot of human palm images, but look at the images that it is generating. So it's not able to maintain the fingers relative sizes in case of the first one. Second one, it's getting distorted. Third one, you can see again the fingers relative sizes that is evident is not reflective. In the next case, it's getting distorted, two fingers are getting mixed and all that, and you can see number of fingers are getting 4 in the last image, and lot of other types of distortions you can see, and this is not even a palm face, the bottom row middle one. So yeah, lot of drawbacks exist in exactly simulating the real data. So all of them are very good quality, but deep down it's not able to reflect the real distribution shown by the actual human palm. Maybe the bottom row second one is closest to the real human palm that we know, right? So I'll end with that. These are the drawbacks, lot of drawbacks, and further this opens up a lot of research directions on these generative models of diffusion and GAN, and I really hope that you can take off, learn this. I hope it helped you learn the theories that are taught in the course better, and hope to see you improving the models further, work on it and so forth. I think this notebook will be made available to you, and you are open to also provide your feedback also and your experience, and hope it was a good experience. Thank you.